Welcome to Grandpa's Late Nights. It's good to have you here again. Pull the blanket up a little, settle your head into the pillow, let your shoulders come down from wherever they've been holding all day. There's no hurry tonight. There's never any hurry here. That's rather the whole point of this little porch we've built together, you and I, out at the quiet end of the evening. So before we go anywhere at all, let me ask you the question I always like to ask. Where in the world are you tonight? Are you somewhere cold, with the window fogged and the radiator ticking? Somewhere warm with the fan turning slow overhead? Are you on a train, watching the dark slide by? On a couch that's seen better years? In a bed that's just the right amount of soft? Wherever you are, whatever the hour is in your corner of the night, I'm glad you came and found me. Tell me about it down below if you like, where you're listening from, and what time it's gotten to be where you are. I read those. They're my favorite part of the whole thing. And while we're getting comfortable, if these slow, late-night wanderings are the kind of thing that helps you let go of the day, a quiet like and a subscribe really do help this sleepy little channel keep its lights on. I'm a small creator, just an old voice and a microphone and a fondness for big ideas at bedtime, and folks like you choosing to stick around is honestly the only reason any of this keeps going. So thank you to those of you who already subscribed. Truly, thank you. You're the reason there's a porch light on at all. Now, I'll try not to make tonight too interesting, though I'll be honest with you, that's a harder promise than usual, because tonight we're going to talk about the end of everything. Not in a frightening way. I'd never do that to you, not here, not at this hour. We're going to walk all the way out to the very last moment the universe ever has. The final event, the last thing that will ever happen anywhere to anything. And we're going to do it so slowly and so gently that if you drift off somewhere in the middle, that's perfectly all right. The end of the universe will keep. It's in no rush either. The ideas will still be here in the morning, and so will I. So here's our fair trade for the night. I'll try not to keep you awake. But if a thought or two does snag you and hold your eyes open a little longer than they meant to stay, well, at least you'll have learned something true about where all of this is going. Now, that seems like an honest bargain to me, a fair trade. Let me start with something strange, something that's happening right now to you while you lie there doing absolutely nothing about it. You are evaporating. I don't mean you're getting older, though you are. And so am I, and there's a tenderness in that we'll come back to. I mean something much odder and much quieter than aging. Right now, lying in your bed, with the blanket over you and your breathing going slow, the atoms that make up your body, the bone and the warmth and the weight of you pressed into the mattress, are very, very slowly leaking themselves back into the dark, letting go of themselves, glowing ever so faintly in a way no eye could ever catch, and turning particle by particle into nothing at all. It would take an unthinkable amount of time. We'll get to just how unthinkable, and the number is so big it stops feeling like a number and starts feeling like a kind of poem. But the point I want you to hold on to, soft and loose, as you lie there, is that it's happening. The same thing that ends stars is, in the smallest imaginable way, happening to you. To the moon, to the chair in the corner of your room and the cup on your bedside table. Everything dense enough to bend the space around it is quietly coming undone on a time scale so long the universe itself is barely getting started. And here's the thing that makes this a story worth lying awake for, just for a minute. We used to think we knew how this all ended. We had a number, a famous one. Scientists wrote it in books and said it on programs and drew it at the far right edge of every chart of cosmic history. And then, just a couple of years ago, 3 quiet physicists in the Netherlands found a flaw in that number. Not a small flaw, a flaw so large it moved the end of the universe closer by an amount I almost can't bring myself to say out loud, because it's that absurd. I'll say it anyway. Gently. You may have heard somewhere along the way that the longest-lived stars in the universe, these patient little embers called white dwarfs, which we'll get properly acquainted with, would survive for something like 10 to the power of 1,100 years. 10 followed by 1,100 zeros. A number so long that if you tried to write it out, 1 zero per second, you'd be writing for longer than the universe has currently existed. That was the old answer. That was the figure on the chart, the white dwarfs, the universe's stubbornest little survivors, holding their tiny lights against the dark for 10 to the 1,100 years. Except they don't. That number is wrong. The real number, the one those 3 physicists worked out, is about 10 to the 78th, 10 followed by 78 zeros. Still unimaginably long, longer than your sleepy mind can really hold, longer than I can hold either. But here is the part that made me sit very still the first time I understood it. 10 to the 78 is shorter than 10 to the 1,100 by a factor of 10 to the 1,022. Let that just sit there a moment, the way a snowflake sits on the back of your hand before it goes. The end of the universe didn't get nudged a little earlier. It got pulled forward by a number with over 1,000 zeros in it. The longest-lived things in all of creation turn out to live a tiny, tiny fraction of as long as we thought. The end is sooner, enormously, dizzyingly sooner. And almost nobody knows this yet because the books haven't caught up, the charts haven't caught up, and the old number is still out there in 1,000 videos and 1,000 classrooms, sitting at the right edge of the timeline, quietly wrong. We're going to make it right tonight, slowly, together. And by the time we're done, or by the time you've drifted off, whichever comes first, you'll understand not just the new number, but why it changed, and the lovely upside-down surprises that come tumbling out of it. Like the fact that the dead moon will outlive almost every black hole in the cosmos. Like the fact that the toughest, densest objects die first, and the flimsy ones outlast them. Like the very last event of all are the single, faint, final flash that ends everything, everywhere, forever. We'll get there, no rush. We've got all the time in the universe. So, let me tell you who found the flaw. It happened at a place called Radboud University in a city called Nijmegen in the Netherlands. A quiet old university town, and there were 3 of them. Heino Falcke. And that name might ring a faint bell for some of you, because Heino Falcke is one of the people behind the very first photograph ever taken of a black hole, that strange orange ring you might remember from the news a few years back. So this is not some fringe figure. This is one of the people who showed us what a black hole actually looks like. And working alongside him, Michael Wondrak and Walter van Suijlekom. 3 names, hold them loosely, there won't be a test. And what they did, in a paper they published in 2023, was something rather brave. They looked at an idea that the great Stephen Hawking had handed down to physics decades earlier, an idea so beautiful and so settled that almost nobody had thought to poke at the edges of it in 50 years, and they found that Hawking, brilliant as he was, had drawn the boundary of his own idea too small. He'd said this strange glowing, this slow evaporation, was a thing that only black holes do. And these 3 said, no. We think this happens to everything. We think the moon does it. We think a dead star does it. We think you do it. But I'm getting ahead of myself, and that's not how we do things here. We don't sprint to the end, we take the long walk. So let me back us all the way up and back to now, back to tonight, to you in your bed, and then let's begin the slow, slow zoom outward through time. Past tomorrow, past your whole life, past the lives of everyone who will ever live. Out and out until the numbers grow long, and the lights start going out one by one. We'll go gently. I'll hold your hand the whole way, in the way an old voice in the dark can hold a hand. Let's begin where every story of the deep future has to begin. With the sun. Right now, your sun is doing the most ordinary thing a star can do. It's burning hydrogen deep in its core, fusing it into helium, and that fusion pushes outward against the crush of its own gravity pulling inward, and the two forces hold each other in a long, steady truce. That truce is what we call a star, a balance. It's been going on for about 4.5 billion years already, and it'll keep going for a good while yet. The sun is, as stars go, comfortably middle-aged, settled, reliable, the kind of star you could set a planet's whole history by, which is exactly what happened. But the truce can't last forever. Slowly, over billions of years, the sun is using up the hydrogen in its core, and when the core's fuel starts to run thin, the balance tips. In about 5 billion years from tonight, the sun will begin to change into something the old astronomers gave a wonderful, swollen name, a red giant. The core will contract and heat, and the outer layers, in response, will billow outward, vast and red and cool, until the sun has swelled so enormously that it swallows the inner planets whole. Mercury gone, Venus gone. The Earth scorched bare or swallowed outright, the oceans long since boiled away into space, the whole familiar little world we've sung songs about reduced to a cinder or to nothing at all. I know it's a sad thing to picture, but hold it lightly, because it's 5 billion years away, and 5 billion years is longer than the Earth has existed so far. No one alive tonight will see it. No one's great-great-grandchildren 1,000 generations down will see it. It's so far off that it's almost a kindness rather than a loss. The Earth will have had a very, very long run by then, longer than it's had already, and it's had quite a run already. And here's the gentle thing about the red giant. It doesn't last either, because a star that's gone red giant is a star in its final act, after it sheds those great billowing outer layers off into space. And it does so almost tenderly, blowing them out into a glowing shell that drifts away like a sigh. What's left behind in the middle is the core, just the core, the dense, hot, glowing heart of what the sun used to be. And that, my friend, is a white dwarf, the very thing this whole story is about, the longest-lived light in the universe. So let me introduce you properly, because you and the white dwarf are going to spend the whole night together. Picture the entire sun, a ball of fire over 100 times wider than the Earth, big enough to hold more than 1 million Earths inside it. And now imagine taking nearly all of that and crushing it down, squeezing it, until it's only about the size of the Earth itself. That's a white dwarf, the mass of a star packed into the volume of a planet. It's so dense that a single spoonful of it would weigh as much as a truck, as much as an elephant. The matter inside is squeezed so tight that the atoms can't even keep their ordinary shape anymore, and they hold themselves up against gravity not by burning. There's no fuel left to burn, but by a strange stubbornness deep in the laws of physics, a refusal of the particles inside to be pushed any closer together. It's a star that has stopped being a furnace and become an ember, a coal pulled from a fire that went out, holding its heat for a span of time so long you and I have no honest way to feel it. And it just sits there, glowing, not burning, cooling. Slowly, over billions and then trillions of years, that little ember radiates its leftover warmth out into the dark, dimming and dimming, going from white-hot to yellow to red to a deep, dull glow until eventually, and this takes so unspeakably long that the universe is nowhere near old enough for even a single one to have finished, it cools all the way down and goes dark entirely. And when a white dwarf has cooled completely black and cold, we give it a new name, a quieter one. We call it a black dwarf, a dead ember, a star's cold cinder drifting in the dark. There aren't any black dwarfs yet, by the way, not a single one in the whole cosmos. The universe simply hasn't existed long enough for even the oldest white dwarf to finish cooling. They're a thing of the future, a thing of the deep, dark future we're walking toward together. Hold that. It's lovely in a strange way that there's a kind of object the universe is destined to have in vast numbers, but doesn't have even one of yet. We're early. We're so very early. So that's where the sun ends up. Red giant in about 5 billion years, then a white dwarf, an Earth-sized ember of crushed down star stuff, glowing and cooling for ages beyond ages. And not just our sun. Most stars in the universe end this way, as white dwarfs. They're the common fate, the ordinary grave of an ordinary star. The sky in the deep future will be littered with them, billions upon billions of cold and cooling embers where the bright stars used to be. Now I want you to feel the time scale here, because it only gets longer from here, and it's good to get used to the stretching of it now while the numbers are still ones we can almost hold. The sun's whole life as a bright star, birth to red giant, is something like 10 billion years. We measure that in billions, 10 to the 9 or 10 in the shorthand of the physicists, where the little raised number just tells you how many zeros come after the 1. 10 to the 9 is a 1 with 9 zeros. A billion? Easy enough. You can almost picture a billion if you squint. But we're going much, much further than billions tonight. So let your mind get loose and soft with the numbers, the way it gets loose and soft just before sleep. Don't try to grip them. Let them flow past like water. 10 to the 9, 10 to the 14, 10 to the 40, 10 to the 67, 10 to the 78, 10 to the 100. Each one isn't a little bigger than the last. Each one is unimaginably bigger, because every step up in that little raised number multiplies everything by 10 all over again. 10 to the 78 isn't 78 times bigger than 10 to the 77, it's 10 times bigger. And 10 to the 77 was already 10 times bigger than the one before it, all the way down. The numbers don't grow, they explode quietly, each one swallowing the last whole. So when I told you the white dwarfs were once thought to live 10 to the 1100 years and now turn out to live 10 to the 78, try, just gently, to feel the cliff between those two. 10 to the 78 is already a number with 78 zeros, and the old number had 1100. That's the difference between a sentence and an entire library, between a single grain of sand and a beach that stretches past the horizon and keeps going for 1,000 more horizons. The white dwarfs lost 1,022 of their zeros, just like that, because 3 people in Nijmegen looked carefully at an old, beautiful idea. But I promised we'd go slowly, and we have a long way to fall before we reach the white dwarf's end. So let's keep zooming. Let's leave the sun behind, a cooling ember now, and pull back to see the whole neighborhood it lives in. Our sun isn't alone, of course. It's one star among a few hundred billion in a great pinwheel of light we call the Milky Way, our galaxy, this slow-turning island of stars that takes the sun something like 250 million years just to circle once. And the Milky Way isn't alone either. It drifts through space alongside a handful of other galaxies, all of them held loosely together by gravity into a little family we call the local group. There's the Milky Way, and there's the great spiral of Andromeda, larger than us and coming our way, and there's a scattering of smaller galaxies orbiting around the 2 big ones like moths around 2 lanterns. And here's something that's already in motion, already happening, slow as continents. Andromeda is falling toward us. or we're falling toward it, which is the same thing. The two great spirals are drifting closer across the dark, and somewhere between 4 and 5 billion years from now, right around the time the Sun is going red giant, as it happens, though by then no one will be on Earth to notice the coincidence. Andromeda and the Milky Way are going to meet. Now don't picture a crash. That's the wonderful thing. When galaxies collide, almost nothing actually hits anything. The stars are so far apart, with such vast oceans of empty space between them, that the two galaxies pass through each other more like two clouds of smoke mingling than like two cars colliding. Stars sweep past stars at enormous distances. Gravity tugs and stretches everything into long, glowing streamers. And over hundreds of millions of years, the whole thing slows and settles and merges. Two spiral galaxies become one great, muddled ball of stars. Some folks have taken to calling the merged result Milkomeda, which always makes me smile, a name like something you'd order at a diner. And it won't stop there. Over a much longer span, somewhere in the range of 100 billion years, 10 to the 11 to perhaps a trillion years, 10 to the 12, all the galaxies of the local group, the whole little family, will gradually fall together and merge into a single vast galaxy. One great island of stars where there used to be many. The neighborhood collapses inward into one home, and I want you to notice the number we've just reached because we've taken a real step out into the deep now. 100 billion to a trillion years. 10 to the 11, 10 to the 12. The universe right now is only about 14 billion years old. 10 to the 10, a 1 with 10 zeros. So when the local group finishes merging, the universe will be roughly 100 times older than it is tonight. We've already walked out past the point where the cosmos is 100-fold older than everything that's ever happened so far. And we have barely begun. We're still in the foothills. The long, dark plain stretches out ahead of us, further than I can show you in one breath, and we'll cross it slowly, the two of us, in the parts still to come. For now, just hold the picture. 5 billion years out, the sun swells and dies and leaves an ember, and Andromeda comes drifting in to merge with our Milky Way. 100 billion to a trillion years out, the whole local group falls together into one great galaxy, alone in its corner of space. And all the while, scattered through it, the white dwarfs are glowing and cooling, those crushed down, Earth-sized embers that we used to think would burn their tiny patient lights for 10 to the 1100 years. But they won't. And in a little while, when you've sunk a bit deeper into the pillow, I'll tell you why. I'll tell you about the flaw 3 quiet people found in Stephen Hawking's beautiful idea, and the strange new rule it gives us. The rule where the densest, toughest things die first, and a dead rock outlasts a black hole, and everything that exists is very slowly glowing itself away into the dark. But the lights aren't out yet, not nearly. There's a whole long dusk still to walk through first, where the last stars are still being born, and the sky still has things in it to see. So let's go there next, you and I, out past the merger, into the long evening of the universe, where the stars begin, at last, to stop. The long evening, that's a good name for it, I think. Picture the merged galaxy hanging there in the black, our Milky Way and Andromeda folded together into one swirl of old light, the way 2 streams become one river, and you can't tell anymore which water came from where. No neighbors left to speak of. 2. The other galaxies have been carried off by the expansion of space itself, drifting past the edge of what we can ever see, until by around 10 to the 12th year, there's nothing in your sky but your own galaxy and a great deal of darkness. A lonely view, but a peaceful one too, if you let it be. And in that long evening, the stars don't all wink out at once. They taper off. The big bright ones, the ones that live fast and die young, those went first, ages ago. What's left burning are the small ones, the red dwarfs, stingy little stars, cool and dim, and impossibly thrifty with their fuel, the way some folks can stretch one pot of soup across a whole week. They burn so slowly that they keep going long after everything flashier has gone cold. They're the last lamps in the house, and even they finally gutter out somewhere around 100 trillion years. 10 to the 14th, if you like the number. And that's the moment the books give a name to. The end of the stelliferous era. The end of the age of starlight. After that, no new star is ever born again, not one. The universe stops making its own light. Let that settle for a moment. Not as something sad exactly, just as something true. There was a beginning to starlight and there is an end to it, and we happen to be living in the thin, bright sliver between the two. Right now, tonight, in your bed, in this exact pocket of time, the lamps are still on. That's worth something. Now, before we walk on into the dark that comes after, I owe you a promise I made a moment ago, and I don't like to leave a promise hanging when someone's trying to sleep. I told you the white dwarfs wouldn't last 10 to the 1100 years after all. I told you somebody found a flaw. So let me tell you who and let me tell you where, because the where is a cozy little detail and I'm fond of it. It happened in a town called Nijmegen in the Netherlands, at a place called Radboud University. The year was 2023, and it wasn't a great army of scientists, it was 3 of them. A man named Heino Falcke. And you may have heard his name without knowing it because he was one of the people who helped take that very first photograph of a black hole, the orange ring around a pit of nothing that went all around the world a few years back. With him, Michael Wondrak and Walter van Suijlekom. 3 people sitting with the math, looking very hard at an idea that everyone thought was finished and settled and dusted off long ago. And the idea they were looking at was Stephen Hawking's, the famous one, the one about black holes glowing. You see, for a long time, we believed black holes were perfectly black. They take in everything, they give out nothing, the door only swings one way. And then in the 1970s, Hawking did something quietly miraculous. He showed that a black hole isn't quite perfectly black at all, that right at its edge, at that one-way door we call the horizon, it leaks, just barely. It gives off the faintest possible whisper of radiation, and over an unimaginable stretch of time, that whisper carries the whole thing away. The black hole evaporates, it shrinks and glows, and at long last, it's simply gone. A stellar mass black hole takes around 10 to the 64th year to do it. The truly giant ones, the supermassive monsters, 10 to the 100th, numbers that don't mean anything to a human heart, but hold them loosely because we'll need them later. So that was the picture. Black holes glow and fade. Everything else just sits there, cold and dead but intact, waiting more or less forever. The white dwarfs, the dead embers of stars like our sun, they'd cool to black dwarfs and then simply persist, patient as stones, until some other slow process got around to them. Maybe 10 to the 1100 years off, a number so long it's almost a joke. Here's the thing those 3 found, the thing that's so simple once you see it, that you wonder how it sat hidden for 50 years. They asked, what is it really that makes a black hole glow? And the old answer was, it's the horizon. It's that one-way door, that sharp edge where space falls in forever. But when they worked through the mathematics carefully, they found the door wasn't the important part. The important part was the bending of space itself, the curve. Any heavy, dense thing bends the space around it. That's just gravity. That's what gravity is. And it turns out that curve alone is enough to coax those faint whispers of radiation into being. You don't need the door. You only need the bend. And do you feel what that does? Because I felt it the first time, lying right where you are. It means a black hole isn't special. It means the glow, the leak, the slow evaporation. And that's not some exotic privilege of the deepest pits in the cosmos. It's a thing that any dense object does. A white dwarf does it. A neutron star does it. The cooling cinder of a dead star does it. The whole universe, every leftover lump of matter in it, is very, very slowly glowing itself away into the dark, whether it has one of those one-way doors or not. Everything is evaporating. It always was. We just never knew. So in 2025, those same three took the rule and ran the numbers on the real survivors, the white dwarfs, the things astronomers literally call the last stable stars the universe will ever have. And the answer came back not 10 to the 1100 years, about 10 to the 78th. I want you to sit with that gap, because it's the whole reason I'm telling you any of this tonight. The old number and the new number, 10 to the 1100 against 10 to the 78. Now both of those are spans so long that your mind just slides right off them, I know, but the difference between them isn't a little trim. Divide one by the other, and what you get is 10 to the 1022. The end of everything moved closer by a factor with more than 1,000 zeros trailing after it. Write a 1 and then keep writing zeros, slowly, one after another, until you'd filled a page and another page, and you still wouldn't be done. That is how much sooner the lights truly go out than we thought they would. Every documentary, every gentle voice that ever walked you to the end of the cosmos before tonight, they all used the old number, the big one. They couldn't help it. It was the best we had. And it was wrong in the friendliest possible way by an amount no human language was built to hold. Now don't let that trouble you. 10 to the 78 is still so far away that it makes the entire age of the universe so far, those 13.8 billion years since the very beginning, look like less than the first soft tick of a clock that's going to run for the rest of forever. Nothing about your night, or your life, or your children's children's children is one whisker closer because of this. It's only that the very last page of the very last chapter got moved up. The story's the same length to us. It just has a real ending now, where before it had a number too big to be real. And here's where it starts to get strange and lovely both at once, and I'll save the best of it for when you're nearly under. Because once you accept that everything glows and fades by how tightly it curves the space around it, by how dense it is, the whole order of things turns upside down. The toughest, densest objects in all creation don't last the longest. They go first, and the flimsy ones, the dead rocks, they linger. There's an object out there, a dead and silent thing that will outlast nearly every black hole in the sky. We'll get to it, we will. But the dark is deep and the night is long, and there's no rush, none at all. So let us walk forward a little into the dark, slowly at the pace the night deserves. You're still where you were. Warm, I hope. The same corner of the world, the same lamp or the same dark ceiling above you. And the universe, right now, is still doing what it always does, burning and spinning and expanding outward at a pace that, if you could see it from far enough away, would look perfectly tranquil. Stars are being born as you breathe. Others are dying in slow silence. The whole vast machine is still very much running. We are, in the grand scheme of things, absurdly early. So early that to call us early is itself a kind of understatement the English language wasn't really built for. But we're going to walk forward anyway, step by step, past everything that's familiar, past everything that's safe and bright, out into the long dark of what comes after. And I promise we'll take it gently. Let's start close to home, because close to home is still almost unimaginably far. In about 5 billion years, our sun, this warm, ordinary yellow star that's been rising and setting for longer than the Earth has existed, longer than anything alive has ever had eyes to see, it begins to change. It's been in the dossier already, so you know the broad strokes. It swells, becomes a red giant, enormous and patient, and it burns through what remains of its fuel. And then, when it has used up everything it can use, it does something rather quiet for a star. It sheds its outer layers, a slow, gorgeous sigh of gas and light into space. And what's left behind, the dense little heart of it, contracts, cools, settles. That remnant is called a white dwarf, and a white dwarf is a remarkable object. Not remarkable in the way a supernova is remarkable, no explosion, no drama, no shockwave rattling through neighboring clouds of dust. A white dwarf is remarkable the way a very old, very dignified thing is remarkable. It is roughly the size of the Earth, but it contains the mass of the Sun. Imagine picking up something the size of a beach ball that weighs what the entire ocean weighs. A teaspoon of white dwarf material would, if you could somehow weigh it here, tip the scales at several tons. It's held together not by the fires that held the star together, but by something called electron degeneracy pressure, which loosely and softly means that the electrons packed inside it simply refuse to be pushed any closer together. The laws of quantum mechanics are holding it up. It is a quantum object in a way, as much as it is a stellar one. And white dwarfs in the old picture of the universe's end were the last survivors, the stubbornest, the universe's longest-lived stars, as the press releases for the new Radboud work put it. That phrase is worth sitting with, the longest-lived stars. They were supposed to be the things that simply refused to leave long after everything else was gone. And, in a sense, that's still true. Just not for as long as anyone thought. But we'll come back to that. Because first we have to watch the rest of the lights go out. The Sun's story, 5 billion years from now, is not unusual. Almost every star in the sky will tell some version of it or something rougher. The massive stars, the great blue-white ones that burn so intensely you can see them from across the galaxy, they'll go out in supernovae, leaving neutron stars or black holes behind. The medium stars, like the Sun, leave white dwarfs, and the small ones, like the red dwarfs, the dim, cool, incredibly frugal little stars that burn so slowly and carefully they can last for trillions of years, they fade too eventually. It just takes longer. And that matters, because the red dwarfs are the last campfires. Here is one of those facts that sounds simple and is bottomless. The last stars stop forming at around 10 to the 14 years, 100 trillion years from now. Not 100 trillion years since the Big Bang. It's 100 trillion years from now. We are currently 13.8 billion years into a universe that will still be making stars 100 trillion years from our right now. That is how early we are. We are so early that if the entire stelliferous era, the era of stars, the whole luminous age in which stars burn and planets form and everything bright happens, if all of that were a single day, we would be about a second and a half in. The stelliferous era, it's a lovely name, isn't it? Stelliferous, star-bearing, and it will eventually end. The last red dwarfs, the smallest and most frugal of all stars, will finally exhaust their hydrogen fuel and collapse into white dwarfs, or sometimes simply into dim, cool, inert little objects. After somewhere around 10 to the 14 years, 100 trillion. And when the last one fades, the sky changes in a way that has no precedent in all the universe's history up to that point. The sky goes dark. Not all at once, of course. There's no single moment where a switch is thrown. It's gradual, the way twilight is gradual, except stretched across billions of years. Star by star, cluster by cluster, the great rivers of light we call galaxies, the Milky Way, Andromeda, the great towers of stars visible to a good telescope on a clear night. They dim. The youngest stars go first, burning bright and brief. The older ones linger. The red dwarfs hold on longest of all, long past the point where anything watching from inside the galaxy would recognize the sky as anything like the one above you tonight. And then, at last, the last red dwarf uses the last of its fuel, and the era is over. The era of burning things ends. Now, there's something I should mention here because the timeline of this is a little layered, and I want to be gentle with it. The light going out in the stelliferous era, the stars stopping, that happens at around 10 to the 14 years. But something else happens slightly before that, cosmologically speaking, that changes what kind of universe those last red dwarfs are living in. Dark energy. You've heard of it, perhaps? Or you've heard the name? It's one of those terms that sounds as though it ought to explain itself, and then, when you look at it closely, turns out to be a polite way of saying something is pushing the universe apart, and we're not entirely certain what. The expansion of the universe is not slowing down the way you might expect gravity to slow it down. It's speeding up. Space itself is stretching faster and faster, and the galaxies that are already far away are getting farther away faster than you'd think. And this has a consequence that, in the very long run, is rather lonely. By around 10 to the 12 years, a trillion years from now, the galaxies beyond our local group will have receded so far, so fast, that light from them can no longer reach us. They will have crossed what's called the cosmic event horizon. They'll disappear, not because they've been destroyed, but because the space between us and them will be expanding faster than light can cross it. They'll be gone for any practical purpose, gone from the observable universe of any being that might, impossibly, be alive to observe it. What's left, visible to a hypothetical future observer, is the merged remnant of the local group. The Milky Way and Andromeda, which are already on a collision course, a slow, gentle collision of vast amounts of empty space over a span of time almost too large to hold, will eventually complete their merging into one great elliptical galaxy. Other nearby galaxies will join or be absorbed, and this merged, settled, ancient object will sit at the center of the observable universe like the last lamp in an enormous dark room. Beyond it, nothing. Just expansion. Just the void between things that can no longer speak to one another. It's a picture that's both desolate and somehow peaceful. The universe has already become most of itself. It's already done the great flowering, the stars and the galaxies, and the whole blaze of the stelliferous era. And now it settles, contracts inward to the local, becomes quiet. And inside that quiet remnant galaxy, the remaining stars are still burning, some of them, for a while yet. The last red dwarfs are still going, in their careful, patient way. Life, if it still exists anywhere by then in any form at all, which is a question for another night, would look up and see a galaxy. But past the edge of it, nothing. A wall of dark and silence. This is the stage that's being set. This is the theatre the rest of our story plays in. And the next act begins at roughly 10 to the 14 years, when even those last red dwarfs finally give out, and the universe enters what the cosmologists call the degenerate era. Degenerate. It's a word that sounds like a judgment, but it isn't meant as one. In physics, degenerate has a technical meaning. It refers to matter held together by quantum pressure, the kind that holds up white dwarfs and neutron stars, rather than by ordinary thermal pressure or the fire of nuclear fusion. Degenerate matter is matter that has settled into its lowest possible energy state, held up by the laws of quantum mechanics alone. It's not decaying, it's not failing, it's simply done burning, and now it's resting on the deepest quantum floor it can find. The degenerate era runs in the old picture from roughly 10 to the 14 years to somewhere around 10 to the 40 years. And during all of that time, the universe is dominated by these quiet, dense remnants, white dwarfs, some of which were once stars like the Sun, some more massive, some less, now cooling slowly. When they cool completely, they become what astronomers call black dwarfs. Not black holes, nothing that dramatic, just cold, dark, dense spheres of crystallized carbon and oxygen, or sometimes oxygen, and neon, sitting silently in the dark, emitting nothing. Invisible? Patient, extraordinarily patient. Neutron stars. These are the remnants left behind by the larger stellar explosions, the supernovae of more massive stars. A neutron star is even denser than a white dwarf. Where a white dwarf is held up by electron degeneracy pressure, a neutron star is held up by neutron degeneracy pressure. It's been compressed so thoroughly that the electrons and protons have merged into neutrons, and the whole object, roughly 20 kilometers across but containing more mass than the Sun, is essentially one enormous atomic nucleus. Hard to imagine. Let me try an analogy. If you could take a mountain, a real one, something like the Alps, and compress it until it fit inside your living room, and then do that again, and again, and again, until the whole thing fit inside a city block, you'd be getting somewhere close to the density of a neutron star. Not quite, but close enough for tonight. And then there are brown dwarfs, not quite stars at all, objects that formed out of the same swirling clouds of gas as stars, but without quite enough mass to ignite nuclear fusion. They glow faintly with their own residual heat, but they never burn, not properly. They're sometimes called failed stars, which feels a little unkind. They're simply a different kind of object. In the degenerate era, these too are present, cooling slowly, having outlasted everything brighter than themselves. This, then, is the degenerate era. A universe of dark, dense, quiet things. Black dwarfs glittering with nothing. Neutron stars spinning slowly in the dark. Brown dwarfs drifting through an empty galaxy with no starlight to reflect. The temperature of the universe dropping toward the lowest it can go. No fusion, no fire, no light. Just mass and density and the deep, patient quiet of quantum mechanics holding things together. It goes on for an almost unimaginable span of time, 10 to the 14 to 10 to the 40 years. If the stelliferous era felt long, and 100 trillion years is long even by any measure, the degenerate era makes it look like a prologue. It is, again, a number so large that naming it is mostly a gesture toward the dark. And during all of this, what did the old picture expect? What did the textbook ending say was happening to the matter in those remnants? This is where the crack in the old story begins. The classical story, the one told in most of the documentaries and most of the gentle late-night explainers before tonight, leaned on a process called proton decay. Protons, you may know the name, they're one of the fundamental building blocks of atomic nuclei. The nucleus of a hydrogen atom is just one proton. Everything heavier than hydrogen has protons in its nucleus. And in the standard picture of particle physics, the very successful, very well-tested collection of rules and particles called the Standard Model, protons are stable. They don't decay, they don't fall apart on their own. A proton, as far as the Standard Model is concerned, lives forever. But there is another collection of ideas further out, less tested, more ambitious, called Grand Unified Theories, GUTS for short. These are attempts to weave together three of the four fundamental forces of nature: electromagnetism, and the strong nuclear force, and the weak nuclear force, into one single unified picture. Beautiful, ambitious theories. And most of them predict that the proton is not in fact stable. that it does decay eventually, with a half-life of at least 10 to the 34 years. Some versions of the theory predict longer, some shorter, but 10 to the 34 years was a common benchmark. 10 to the 34 years, that's 100 billion, trillion years, give or take. A number already so large that placing it in the middle of the degenerate era doesn't seem outrageous. Not yet. Now, if proton decay exists, then during the degenerate era, the protons inside those quiet white dwarfs and neutron stars are slowly, one by one, decaying, falling apart into lighter particles that then radiate away as heat and light. Over the span of the degenerate era, enough protons would decay that the structure of the remnants would slowly come apart from the inside. Matter would gradually disintegrate, not dramatically, not in a flash, but grain by grain, particle by particle, proton by proton, over timescales that would make a human mind go blank, trying to picture them. And when the proton decay process had run its long, patient course, somewhere around 10 to the 40 years or beyond, most of the matter in the universe would be gone. Not transformed into something interesting, just radiated away into dim photons and neutrinos, the waste heat of protons giving up the ghost. That was the old backbone of the story. Proton decay dismantles matter. White dwarfs don't survive it. Nothing does. But here is the problem, the rather large and patient problem that has been sitting in the middle of the story all along. Nobody has ever seen a proton decay. Not once. Physicists built an enormous underground tank of water in Japan called Super Kamiokande. 50,000 tons of ultra-pure water, surrounded by thousands of sensitive light detectors, buried under a mountain to shield it from cosmic rays that might confuse the signal. They have been watching for decades for the tiny flash of light that a decaying proton would produce. And they haven't seen one. Not one. Every year that passes, every year no proton decays, the lower bound on the proton's lifetime gets pushed higher. Super Kamiokande has now pushed it past 10 to the 34 years, which is already past where many grand unified theories predicted it should have been. The most constrained versions of those theories are now under real pressure. It's possible proton decay happens, and the timescale is just longer than we can yet probe. It's possible that a version of the grand unified theory with a longer predicted half-life is correct. It's possible that proton decay is real and simply beyond our current reach. Physicists would not bet against it entirely. But it is not confirmed, it is not observed, it is, as of tonight, a prediction that has not been validated. And the classical cosmic timeline leaned on it. The white dwarfs in the old story survived as long as they did because proton decay would eventually get them. But proton decay at 10 to the 34 years was already so far in the future that it barely bothered the degenerate era in any practical sense. And then came the question of what happened to the very last remnants, the ones that managed to survive even the proton decay timescale. The answer, in the old picture, was strange, because if proton decay is very slow or absent, then some processes within the remnants, slow quantum mechanical reactions called piconuclear fusion, in which nuclei tunnel through barriers and fuse even at very low temperatures, could in principle convert white dwarfs over extraordinarily long timescales into blobs of iron. The iron nucleus is the most stable arrangement of protons and neutrons, the lowest energy state available. And eventually the thought went, a white dwarf might slowly and quietly convert itself into iron and then sit there. And then what? And then the number that appeared in the old textbooks. 10 to the 1,100, say it slowly. 10 to the 1,100. A 1 followed by 1,100 zeros. That's not a typo, and it's not an exaggeration. That was the figure that appeared in the technical literature for how long white dwarfs in the most extreme scenarios, might persist if proton decay never happened. The piconuclear conversion processes and the quantum tunneling of entire remnants toward lower and lower energy configurations created timescales of this magnitude, 10 to the 1,100 years. A number so large that the entire age of the universe, written in comparison, is not even a footnote. It is not even visible. The current age of the universe is roughly 10 to the 10 years. Against 10 to the 1,100, it is a rounding error so small that to call it a rounding error is already generous. This was the endpoint that those documentaries landed on. That gentle voice in the dark, walking you to the end of everything, would eventually arrive at the black hole era, dominated by the last remaining black holes, slowly evaporating via Hawking radiation, and then past that, the remnants of the degenerate era hanging on impossibly until 10 to the 1,100 or beyond, when the very last configurations of matter finally settled into nothing useful. And then heat death, maximum entropy, no usable energy gradients anywhere, the universe at last and forever at rest. It's a picture that has a certain grandeur to it, even a certain peace. The universe, in that telling, has all the time it could possibly need. It is in no hurry. It is never in a hurry. The end is so far away that the word end barely applies to it. It just has an asymptote, a slow reaching toward a state of rest so gradual that calling it an end feels almost like poetry. But then came 2023, and 3 physicists at Radboud University in Nijmegen, and we'll spend real time with them and their work in the next part of tonight, looked at a detail in the mechanism behind Hawking radiation, and they found something that the old picture had missed, something that didn't require proton decay, something that didn't require grand unified theories or quantum tunneling or piconuclear fusion or anything unconfirmed, something that followed quietly and rigorously from general relativity and quantum field theory, the 2 great pillars of modern physics that are individually among the most tested and confirmed theories human beings have ever produced. And what they found is that the number 10 to the 1,100 is wrong. Not a little wrong. Not wrong by a factor of 10 or 100 or a billion. Wrong by an amount that, when you write it out, looks like a mistake. The new number for the evaporation of white dwarfs, the universe's most stubborn, longest-lived stars, is roughly 10 to the 78 years, and the difference between 10 to the 78 and 10 to the 1,100 is 10 to the 1,022, a factor with over 1,000 zeros. The end of the universe just moved up by a factor with over 1,000 zeros. And here, on the edge of that discovery, is where I want to leave us for just a moment. The dark outside is very dark. The quiet is very quiet. The numbers are very large. And something about the idea that even our best picture of the very end of everything was that far off, not because of carelessness, not because of bad science, but because of a mechanism no one had thought to apply in quite this way. Something about that feels right for bedtime in the strangest possible sense. It's a reminder, gentle and immense, that the universe is always larger, always stranger, always slightly different from the map we've drawn of it. The map is never quite the territory, not even when the territory is eternity. So, the degenerate era. The black dwarfs and neutron stars and brown dwarfs arranged in their long, patient rows in the dark of the post-stellar universe. The old story said they had nearly forever. The old story said proton decay would slowly and quietly dismantle them, if it happened at all, and that the remnants would linger in some form until numbers so large they stop meaning anything. But the new story, Radboud's story, the one that will occupy us now as we go deeper into the night, says something different. It says the mechanism that makes black holes glow is not a privilege of black holes. It says space-time curvature alone, the bending and warping of space around any sufficiently dense object, is enough to do what Hawking thought required a horizon. It says these quiet remnants of the degenerate era, these patient survivors, are not actually patient. They are glowing too. Faintly, unimaginably faintly, far too faint to ever detect in any era of the universe, but glowing nonetheless. And glowing means losing mass. And losing mass, given enough time, and there is, after all, enough time, means disappearing. The black dwarfs will go, the neutron stars will go, and the white dwarfs, the last and most flimsy of the dense remnants, the ones that in the old picture had the best chance of surviving longest, will go at 10 to the 78 years. Not 10 to the 1,100, 10 to the 78. The effective end of the universe, the moment when the last stable object made of ordinary dense matter finally evaporates into nothing, just moved forward by a factor with 1,000 zeros. And that is the gift, if you can call it a gift, that 3 physicists in the Netherlands gave to the cosmic timeline in 2023 and 2025. Not a revision of the physics exactly, not a new theory pulled from thin air. A more careful application of physics we already had. A quiet correction to a picture that had been, without anyone quite noticing, built on a foundation that needed looking at. It's still very far away, mind you, 10 to the 78 years. There is no urgency here, none at all. If you fell asleep right now, and please, feel free, there's truly no hurry, and slept until 10 to the 78 years from now, you would miss nothing of consequence to your evening. But the picture has changed. The picture of the very end has changed. And because I think there's something deeply, quietly beautiful about knowing the real shape of things, even the shape of the very last things, I want to make sure we get there together. And we will. We will. But for now, let's just stay here, in the soft dark of the degenerate era, in this universe of quiet, dense, cooling things. The black dwarfs drifting, the neutron stars slowly spinning. The brown dwarfs, those gentle failed stars, sitting in the dark of a galaxy that no longer has any light to call its own, except what it makes itself faintly in the last remnant fires of its most patient objects. It's a universe that has already done everything it set out to do. Already made all the stars and planets and anything that might have grown on them. Already expanded and merged and collided and settled. And now it rests in the vast and patient dark for a span of time so long that the word long isn't really the right word anymore, but it is not resting forever. It is glowing faintly. In a way it didn't know about itself until very recently, and that glow, that almost imperceptible, physics-required, horizon-unnecessary glow, is the mechanism that will bring everything to its close. We'll get to how. We'll get to why density betrays you and why the toughest things die first, and what the moon has to do with all of it. That's coming. It's all coming. For now, though, just rest in the dark. The universe is very old, and it's getting older still. And you are somewhere in the very earliest part of its story, warm and breathing and quietly marveling at how far the road goes. That's not a bad place to be on a night like this. And so let's talk about the glow. Let's talk about where it actually comes from and why it took until 2023 for anyone to realize that what Hawking had discovered wasn't as exclusive as everyone had assumed. Stephen Hawking published his result in 1974 and then again in fuller mathematical form in 1975. It was, by any measure, one of the most surprising things anyone had ever written down in physics. Black holes, he showed, are not truly black. They radiate. They lose mass slowly over inconceivable spans of time, bleeding away into the surrounding universe as a faint thermal glow. Hawking radiation it was called, and the name stuck, and the idea spread. And eventually it became one of those things that serious physicists accepted, even without ever being able to test it directly, because the mathematics were just too elegant, too internally consistent, too clearly right. The mechanism he described went something like this. In the vacuum of space, and here I should say that the vacuum of space is not actually empty, or at least not empty in the way you might be picturing, not the blank and featureless nothing of an unused room. In the vacuum of space, pairs of particles are constantly flickering into existence and then almost immediately annihilating one another again. They are called virtual particles. They are a consequence of quantum mechanics, which permits this kind of fleeting borrowing from nothing so long as the borrowed energy is paid back quickly enough. Under ordinary circumstances, both particles in a pair appear together and vanish together, and nothing net happens. But near the event horizon of a black hole, something different occurs. The horizon is the boundary, the point of no return, the place where the gravitational pull becomes so overwhelming that not even light can escape. And because space-time is so violently distorted right at that boundary, it can happen that when a virtual particle pair appears there, one of the two particles falls inward across the horizon and is swallowed by the black hole, while the other one escapes. The one that escapes becomes real. It takes energy from the gravitational field to do so, and the black hole, in providing that energy, loses a tiny, almost unimaginably small amount of its mass. This keeps happening again and again, particle after particle escaping at the horizon, each one carrying away a sliver of the black hole's mass. Over time, over truly extraordinary spans of time, the black hole shrinks, and eventually, after a period that scales as the cube of its mass, that was worked out in detail by Don Page in 1976, building on Hawking's original calculation, it is gone. Don Page's contribution is worth a moment of appreciation. He was a graduate student of Hawking's, and the precise evaporation time calculations, the ones that gave us the numbers we actually use when we talk about how long a black hole lasts, those were in large part his work. A stellar mass black hole, something like 10 times the mass of the Sun, the kind left behind when a massive star collapses, would take on the order of 10 to the 64 years to fully evaporate. Written out, that's a 1 followed by 64 zeros. 10 to the 64 years. A supermassive black hole, something like 100 billion times the mass of the Sun, the kind that lurks at the center of a large galaxy, would take on the order of 10 to the 100th power years, which physicists write as 10 to the 100 and sometimes shorten to a googol, because the mathematician Edward Kasner's 9-year-old nephew coined that word, and it turned out to be useful. 1 followed by 100 zeros. These were the numbers everyone used. These were the numbers you'll find in the classic timeline videos, in the popular science books about the far future, in the lectures and the articles. The last black holes evaporate somewhere around 10 to the 100th power years, and after that there's nothing left but the faint warmth of maximum entropy, the universe in its final state of perfect, useless equilibrium. That was the ending. That was the answer to the question of what happens last. And it was built on an assumption so deeply embedded in the Hawking radiation picture that almost nobody thought to question it. The assumption was this: the event horizon is essential. The horizon is the thing that makes it work. You need that boundary, that point of no return, that place where space-time becomes a one-way door, in order for the particle pair to be separated and for one to escape. Without the horizon, there is no Hawking radiation. Without the horizon, the object just sits there, radiating nothing, lasting forever. Or at least until something else dismantles it, some other process, proton decay perhaps, or slow quantum tunneling, or the endless patience of thermodynamic fluctuations. White dwarfs don't have event horizons, neutron stars don't have event horizons, the moon doesn't have an event horizon, you don't have an event horizon, so none of these things would radiate and none of them would evaporate by Hawking's mechanism, and they would simply persist in the dark for as long as whatever other process came for them eventually took. And for white dwarfs, that upper bound was estimated at somewhere around 10 to the 1100th power years, 10 to the 1100, a number so large it cannot really be meaningfully compared to anything. It's larger than 10 to the 100 by a factor of 10 to the 1000th power. It's a number that makes the current age of the universe look like a single Planck time in comparison, which itself is an absurd understatement. It's a number that is large in the way that the concept of largeness eventually folds back on itself and becomes meaningless. White dwarfs, the universe's longest-lived stable stars, would last essentially forever. Until 2023, that was where the story ended. Then 3 physicists at Radboud University in Nijmegen in the Netherlands sat down with the mathematics and asked a question that was, in retrospect, obvious. They asked, is the event horizon really doing the essential work here, or is it the curvature of spacetime that matters? Their names are Michael Wondrak, Walter van Suijlekom, and Heino Falcke. You may know Heino Falcke's name from a different context. He was one of the driving forces behind the Event Horizon Telescope, the international collaboration that produced the first actual image of a black hole's shadow, the one that appeared in 2019 and was on the front page of what felt like every newspaper in the world. A dark circle ringed in orange light, the shadow of the supermassive black hole at the center of the galaxy M87. Falcke helped make that image possible. So when he and his colleagues started asking hard questions about the foundations of Hawking's framework, they were doing so with a very thorough working knowledge of what black holes actually are and how space-time behaves around them. The paper they published in 2023 appeared in Physical Review Letters, Volume 130, Article number 221502. Its title was Gravitational Pair Production and Black Hole Evaporation. And what it argued was that the separation of virtual particle pairs, and the event that creates the radiation, doesn't actually require an event horizon. It requires space-time curvature. Let me try to say that again in slightly different words, because it's the hinge on which everything else in this part of the story turns. In Hawking's original picture, the horizon is the mechanism. The horizon is what pulls the particle pair apart, what allows one to escape and one to fall in, what converts the virtual into the real. Without the horizon, the pair just pops into existence and vanishes again, and nothing escapes. What Wondrak, van Suijlekom and Falcke showed is that the curvature of space-time itself can do this work. Not the horizon specifically, the curvature. The way that a sufficiently massive, sufficiently dense object bends the fabric of space and time around it. And the crucial point is that you do not need a horizon for curvature. Every massive object curves space-time. Every dense object, a white dwarf, a neutron star, a large asteroid, a human body, curves space-time, at least a little. A horizon is one extreme case of curvature, the case where the curvature becomes so severe that escape becomes impossible. But curvature is the general phenomenon, and the horizon is just a particular limit of it. Think of it this way if it helps. Imagine you're rolling a ball across a rubber sheet, and the sheet is stretched and dimpled by a heavy object sitting at its center. Near a very massive thing, the sheet dips steeply downward, and if you roll the ball close enough to the center, it disappears into the dip and never comes back. That disappearance point, the point of no return, is the horizon. But even far from that disappearance point, the rubber sheet is still curved. The ball still follows a bent path. The space-time geometry around any massive object is curved, just less extremely so as you move away from very compact, very dense things. What the Radboud team showed is that this curvature, even at the level present around objects that don't have horizons, is enough to drive gravitational pair production, enough to pull virtual particle pairs apart, enough to convert some of them into real particles that carry energy away from the object. The rate is tiny, incomprehensibly tiny, far smaller than the already incomprehensibly tiny Hawking rate for stellar mass black holes. But it is not zero. And in physics, not zero and zero are very different things, even when the difference is otherwise impossible to measure. Because if the rate is not zero, then given enough time, and here we have an essentially unlimited supply of time, every object that curves spacetime will eventually radiate away its mass. Every dense body is, in this framework, evaporating, slowly, almost imperceptibly, but evaporating. A horizon is sufficient for this process, but it turns out it is not necessary. That single shift from the horizon is the mechanism to the curvature is the mechanism, and the horizon is merely one strong example of it, is what changed the ending of the universe. The team followed up in May of 2025 with a paper in the Journal of Cosmology and Astroparticle Physics, sometimes shortened to JCAP. That paper applied the new framework directly to stellar remnants, to white dwarfs, to neutron stars, to the objects that actually populate the degenerate era. And it derived finite evaporation lifetimes for all of them. Finite, not approximately forever, not we'll park them near 10 to the 1100th power and call it good. Finite, specific, calculable. The numbers that came out were extraordinary in several directions at once. White dwarfs, the universe's longest-lived stable stars, the objects that were supposed to sit in the dark for 10 to the 1100th power years before anything meaningful happened to them. White dwarfs evaporate, in the new framework, in roughly 10 to the 78th power years. 10 to the 78. Now I want to be careful to let that number breathe because it is still an enormous number. 10 to the 78 years is a 1 followed by 78 zeros. The current age of the universe is roughly 14 billion years, which is about 1.4 times 10 to the 10th power. 10 to the 78 is incomparably larger than that. If you wrote out 10 to the 78 in full, and you tried to read it as a number of years, you would run out of meaningful language long before you finished. The universe could have lived and died 1,000,000 trillion times over in a span of 10 to the 78 years. It is not a short time. But 10 to the 78 is not 10 to the 1100th power. And the difference between those two numbers is so extreme that it requires a moment of careful attention to absorb. 10 to the 1100th power divided by 10 to the 78th power is 10 to the 1022nd power. Written out, that exponent has over 1,000 digits. It is the factor by which the new estimate of white dwarf lifetime is shorter than the old one. The end of the universe, as defined by the last stable star disappearing, was moved forward by a factor that itself has over 1,000 zeros. The Radboud team's press release put it plainly. The new result cuts roughly 1,000 orders of magnitude off the expected lifetime of the last stars. 1,000 orders of magnitude. That's what the event horizon assumption was hiding. That's what gets released when you look at the mathematics carefully enough to see that the curvature doesn't need the horizon to do its work. Now here is where it gets strange. Not just large number strange, but conceptually, intuitively strange, because the new framework also told us something about the order in which things die, and the order is exactly backwards from what you'd expect if you were thinking about it naively. You might expect that the densest, most compact, most gravitationally intense objects would be the most robust, that the sheer density of a neutron star, a star with the mass of the Sun or more, compressed into a sphere, only about 20 kilometers across, so dense that a teaspoon of its material would weigh something like 10 billion tons on Earth. You might expect that this extraordinary density, this stubborn solidity, would make the neutron star the last thing standing, the toughest object, the one that takes the longest to go. But the new mechanism inverts that intuition completely, because if the driver of evaporation is space-time curvature, and if curvature is higher around denser objects, then denser objects radiate faster. The more tightly you pack your mass, the more severely you bend the space-time around you, and the more vigorously you drive gravitational pair production. The neutron star's density, which makes it seem so formidable, so impossibly solid, is precisely what makes it lose mass faster than the flimsier white dwarf sitting next to it in the dark. A neutron star evaporates, in the new framework, in roughly 10 to the 67th power years, 10 to the 67, which is earlier, significantly earlier, 11 orders of magnitude earlier, than the white dwarf's 10 to the 78. The neutron star goes first. The toughest stellar remnant dies before the more diffuse one. Density betrays it. And now let's add the black holes back in, because this is where the comparison becomes genuinely revelatory. A stellar mass black hole, 10 times the mass of the Sun, say, the kind that forms when a large star collapses, has, in Hawking's original framework, an evaporation time of roughly 10 to the 64th power years. That's from the T, proportional to m³ scaling law, where T is the evaporation time and m is the mass. Don Page worked this out carefully, and the numbers have been cited and checked and refined since, and 10 to the 64th is a reasonable figure for a stellar mass black hole. And now notice something remarkable. A neutron star which has no event horizon, which has no singularity, which is just extraordinarily dense, ordinary matter, evaporates by the Radboud mechanism in roughly 10 to the 67th years. A stellar mass black hole, which does have a horizon, evaporates by Hawking's mechanism in roughly 10 to the 64th years. Those two numbers are within 3 orders of magnitude of each other, which is to say, a neutron star and a black hole of similar mass go on roughly similar timescales. Not exactly the same, but strikingly close. Strikingly close, given that one of them has an event horizon and one doesn't. Strikingly close, given that in the old framework, the neutron star was supposed to last essentially forever, while the black hole ticked down toward 10 to the 64. This is one of the paper's most counterintuitive and, in my view, most elegant findings. The horizon turns out not to be as special as it seemed. Both the black hole and the neutron star of comparable mass are engaging in a similar kind of physics, curvature-driven pair production, with similar results. The black hole's horizon is, in some sense, just a particularly efficient version of the same gravitational curvature that drives radiation from the neutron star. Nature is using the same tool in both cases. One just has a boundary and one doesn't. If you were waiting in the dark of the degenerate era and you had instruments sensitive enough to detect this radiation, and nothing would be that sensitive, but just imagine, you would see the neutron stars going dim very slowly, their mass bleeding away into the dark. And not far behind them, the stellar mass black holes doing the same, through their horizon rather than their curvature, but on a similar schedule. And later, significantly later, the white dwarfs following, their lower density making them slightly more durable, so that they outlast both. The order from shortest lived to longest lived among these classes runs roughly like this: stellar mass black holes and neutron stars at 10 to the 64 to 10 to the 67 years, then white dwarfs at 10 to the 78, and the old white dwarf estimate of 10 to the 1100th power? That was the answer to a different question. What would happen to a white dwarf if the only process available to dismantle it were proton decay or some other exotic particle physics event. The Radboud mechanism doesn't need any of that. It doesn't need proton decay to be real, which is fortunate because, as we've mentioned, proton decay has never actually been observed. Super Kamiokande in Japan, which is among the most sensitive instruments ever built for detecting such a decay. A vast underground tank holding 50,000 tons of ultra-pure water, lined with enormous photomultiplier tubes waiting for a single proton anywhere in that water to spontaneously fall apart. Super Kamiokande has been running for decades and has never seen it. The lower bound on the proton's half-life, from those non-observations, has been pushed past 10 to the 34th years. The proton might decay. Grand unified theories suggest it should. But it hasn't been caught doing it yet, and the classic timeline leaned on it heavily to explain how matter eventually comes apart. The Radboud mechanism doesn't lean on it at all. It says, even if protons never decay, even if every proton that exists today is still perfectly intact 10 to the 78th years from now, it doesn't matter. The gravitational pair production mechanism will have already evaporated the white dwarfs that those protons compose, long before any spontaneous proton decay would be relevant. This is one of the quietly important aspects of the 2025 result. It offers a route to the end of structured matter that doesn't depend on a particle physics prediction that remains stubbornly unconfirmed. The universe has a way of winding down that is grounded in what we know, in general relativity and quantum field theory, rather than in what we hope or expect to eventually observe. It's a more robust ending, a more securely founded one, which, in a certain light, is either reassuring or a little unsettling, depending on what you'd been hoping for. Now let's add one more object to this picture, one that you wouldn't expect to be part of this conversation at all. The moon. Our moon, the familiar one. The one you might be able to see through the window tonight, if the clouds are thin enough. The one that's been there for about 4.5 billion years, pulling at the tides, holding the Earth's axis stable, shining borrowed light down onto every version of this planet that has ever existed. The moon is not dense in the way a neutron star is dense. It is not gravitationally intense in the way a white dwarf is intense. It is, as far as the physics of extreme spacetime curvature goes, relatively mild, a modest rocky object. Interesting, beautiful, familiar, but by cosmic standards not particularly exotic. And yet, the Radboud team computed the evaporation timescale for objects like the moon, as an illustrative example, to make the mechanism tangible and to show that it truly applies to everything with mass, not just to the remnants of dead stars. The moon, by this mechanism, would take roughly 10 to the 90th power years to evaporate. 10 to the 90. And now remember, stellar mass black holes evaporate in roughly 10 to the 64 to 10 to the 67 years. The moon outlasts them by a considerable margin. A dead rock, modest by stellar standards, persists in the dark of the far future for longer than objects that swallow light and bend the universe around them, simply because the moon is so much less dense that its space-time curvature is far gentler, and the pair production rate around it is far lower, and so it loses mass far more slowly, and it lasts far longer. 10 to the 90 years for the moon, against 10 to the 67 for a neutron star, against 10 to the 64 for a stellar black hole. The moon outlives both by a factor of 10 to the 23 or so. The mass of a neutron star or a stellar black hole compressed into a sphere 20 kilometers across, or smaller, dies tens of orders of magnitude sooner than a ball of rock, 400,000 kilometers from where you're lying right now. Density is a kind of brevity in the very long run. The team also computed, as an illustrative extrapolation, the time scale for a human body, a human being treated as a dense object. which we are in the same sense that a rock or a planet is a dense object relative to the surrounding vacuum of space, would take on the order of 10 to the 90th power years to evaporate. About the same order as the Moon, which makes a certain sense because both objects are of roughly similar density by the standards of this mechanism. You are slowly evaporating at a rate so fantastically small that no instrument built or imaginable could detect it. You will lose more mass to breathing than to this process in the next 100 years, and in the next 100 million years, and in the next 100 trillion years. But eventually, if you waited long enough, 10 to the 90 years, there would be nothing left. That figure was computed partly to make the mechanism feel real, to make it clear that this isn't just an abstract property of exotic astrophysical objects. Every massive thing in the universe is subject to this. Every warm body, every cold rock, every remnant star, every wandering planet. All of it slowly returning to radiation over timescales so vast that they make the stellar evaporation numbers we've been discussing look comparatively brief. It also changes what the degenerate era looks like, conceptually. We described it earlier as the era of the neutron stars, the white dwarfs, the cooling black dwarfs, all of them drifting in the dark. The standard picture treats that era as a kind of patient waiting room where matter simply sits until some other process, proton decay, quantum tunneling, some thermodynamic fluctuation, eventually does something to it. The new picture says, no, even in the degenerate era, matter is leaving. Slowly, yes. Invisibly, yes. But the exit is already underway. The neutron stars are radiating. The white dwarfs are radiating. Everything that has mass and curves, space-time is, in the faintest possible way, paying its own existence back to the vacuum, particle by particle, over timescales that stretch to 10 to the 78 years. There is no stable equilibrium. There is only an extraordinarily slow dissolution, and the order in which things dissolve is not the order you'd have predicted based on which objects seem most durable or most extreme. The neutron stars, paradoxically tougher and shorter-lived, go before the white dwarfs. The stellar mass black holes, which we once thought would be among the universe's most enduring objects, are gone before the Moon. The familiar, modest, stony Moon has completed its own evaporation. Think about that for a moment. When the last stellar mass black hole in the universe has evaporated, has given its final brilliant little burst of Hawking radiation and vanished, the Moon, or what was once the Moon, or the moon mass remnant of rock drifting in whatever space is by then, still has most of its existence ahead of it. The black hole is gone. The Moon lingers. It's a reordering of cosmic mortality that took us until 2023 to understand. Now, there is one class of object we haven't fully addressed yet. One class that does survive longer than all of this. One class that sits at the far end of even the new timeline. The supermassive black holes. These are the giants, the ones that lurk at the centers of galaxies, or rather, that lurked at the centers of galaxies, because by the time we're talking about 10 to the 78th years, there are no galaxies anymore, in any meaningful sense, just dispersed remnants and wandering objects in an expanding void. The supermassive black holes are the ones whose mass is so enormous, whose Hawking evaporation time is so extended, that they simply outlast everything else. A supermassive black hole with a mass of around 100 billion solar masses, which is roughly in the range of some of the largest known black holes, evaporates, by the standard Hawking calculation, in roughly 10 to the 100th power years, a Google years. And for the very largest black holes, the most extreme gravitational monsters at the centers of the largest galaxies, the figure stretches higher still, to something like 10 to the 108th power years, 10 to the 108. Even in the new Radboud framework, these figures hold, because the new mechanism is most significant for objects that don't have horizons. For objects that do have horizons, for black holes, the standard Hawking result is still the dominant process. The curvature-driven pair production the Radboud team describes is, for black holes, essentially equivalent to or absorbed into the Hawking picture. The major correction the 2025 paper introduces is for the horizonless objects, the neutron stars, the white dwarfs, the rocky bodies. For the supermassive black holes, 10 to the 100 to 10 to the 108 years remains a valid estimate. So after the white dwarfs have gone, after 10 to the 78 years have passed, and the last of the cooling black dwarfs has radiated itself into nothing, the supermassive black holes are still there. Diminished, perhaps. Slowly shrinking, but present. Real. Occupying whatever space now means in an expanding, largely empty universe, separated from one another by distances so vast that even light, traveling at the speed light travels, would never reach from one to another before each was already gone. They sit there in the dark, alone, each one a remnant of an entire galactic center, a gravitational relic of a structure that was once millions of light years across, now compressed into a single object, still slowly shrinking, still radiating very faintly in the Hawking glow. And they shrink very slowly. And as they shrink, the evaporation rate changes because Hawking radiation gets hotter and more energetic as the object gets smaller. The relationship goes the other way from what you might expect. As a black hole loses mass, its Hawking temperature rises. A large black hole is very cold, radiating very low energy photons. A small black hole is much warmer. A very small black hole is hot. So the supermassive black hole, as it evaporates over 10 to the 100th power years, is spending most of that time in a long, cool, almost imperceptible glow. For most of its existence, the radiation it emits is at a temperature barely above absolute zero. Colder, in fact, than the cosmic microwave background is today, which means that in the early universe, it would actually have been absorbing more radiation than it emitted. It is only as the universe cools further, as the CMB temperature drops below the black hole's Hawking temperature, that the black hole begins to lose mass on net. And then, near the very end of its life, something changes. The black hole has been shrinking for a near eternity. Its mass is now very small compared to what it once was. Its Hawking temperature has been rising for all of that time, and as the final phase approaches, the evaporation accelerates. The smaller it gets, the hotter it runs. The hotter it runs, the faster it loses mass. The faster it loses mass, the smaller it gets. It is a runaway, a cascade, feeding on itself faster and faster as the last mass disappears. The end is not a gentle fade. It is not a slow, peaceful dimming into darkness. The final moments of any evaporating black hole, and this was known from Hawking's original work, it is not changed by the Radboud extension. Well, the final moments are a burst, a flash, the brightest instant in the entire history of that object, in the entire history of that region of space. And when the most massive black hole in the universe reaches that final moment, the last supermassive black hole, the most enduring object that will ever have existed, having outlasted every star, every planet, every neutron star, every white dwarf, every moon-like body, every stellar mass black hole that ever formed. When that last black hole reaches the end of its evaporation, there is a brief, bright burst of high-energy radiation, and then there is nothing. Not nothing for a while, waiting for the next thing to happen. Nothing permanently, nothing as a final condition. The last structured object in the universe has converted itself into radiation, and that radiation has spread out and redshifted and thinned in the expanding void, and there are no more gradients of energy, no more concentrations of mass, no more objects to point to and say, that there is a thing. There is only the faint, uniform warmth of maximum entropy, the heat death that thermodynamics always promised. But the Radboud result has sharpened this picture considerably. It has told us that the structured era of the universe, the era in which anything we might recognize as an object still exists, ends not at 10 to the 1100th power years, but at roughly 10 to the 100 to 10 to the 108th power years, governed not by the survival of white dwarfs into nearly forever, but by the final evaporation of the most massive, supermassive black holes. The white dwarfs are gone by 10 to the 78. The neutron stars are gone before that, at 10 to the 67 or so. The moon mass objects are gone by 10 to the 90. And then the supermassive black holes carry on, alone in the dark, slowly, so slowly, shrinking until the last one reaches its final moment somewhere in the neighborhood of 10 to the 100th to 10 to the 108th power years, and emits its last burst and is gone. That burst is the last event. Not just the last astrophysical event, the last event in the history of the universe. The final thing that happens before nothing ever happens again. A single, faint flash. Bright for an instant relative to nothing, then nothing. It lasts perhaps a fraction of a second in its most intense phase. After a duration measured in numbers with 100 digits or more, the entire history of everything that has ever existed, every star, every planet, every civilization that ever was or could have been, every black hole that formed and grew and endured, all of it is preamble to this one moment. And then the moment passes. The loneliness of that image is part of what makes it so arresting, I think. It's not a catastrophe. Nothing explodes, nothing collapses, nothing dramatic happens to bring it about. The universe doesn't end in violence or fire or collision. It ends in the quiet completion of a process that began in the gravitational curvature of a dense object, a process that has been running, almost imperceptibly, below the threshold of any possible detection since the very beginning of the object's existence. Every black hole that ever formed was already on this trajectory. Every neutron star, every white dwarf, every rocky body drifting in the dark. All of them were always doing this. We just didn't know the mechanism was universal until 3 physicists in Nijmegen wrote a paper and submitted it to Physical Review Letters in 2023. The ending was always already underway. It just took us until now to read it correctly. And so we come to the part of the story that is, in a way, the strangest. We've walked a long way tonight. We started with the sun and the quiet end of familiar things. We watched the last stars cool. We followed the logic of the degenerate era, the long patience of white dwarfs and neutron stars, the old assumption that matter might persist almost indefinitely. We met 3 physicists in Nijmegen who changed the numbers, and we arrived at the mechanism, a curvature-driven pair production, the idea that space-time itself, bent sufficiently, produces radiation from any dense body whether or not it has a horizon. No event horizon required. The universe does not play favorites. Now we need to sit with some specific things, specific numbers, specific objects, the kinds of images that, if you let them settle, have a way of rearranging how you hold the universe in your mind. Let's take the moon. Right now, wherever you're lying, if you were to go to a window and look up, or imagine looking up, you might see it, or know it's there, on the other side of the planet, doing what it has always done, pulling the oceans, keeping time. That familiar, battered, cratered disk that has hung in Earth's sky for about 4.5 billion years. The moon has no atmosphere, no magnetic field to speak of, no geological activity, no volcanoes replenishing its surface, no weather to wear it down. It is, in many senses, already done. A remnant, a record of impacts from the early solar system preserved in rock and silence. And yet, under the Radboud mechanism, under the framework that Wondrak, van Suijlekom and Falcke laid out and applied to dense bodies in their 2025 paper in the Journal of Cosmology and Astroparticle Physics, the Moon is not simply sitting there, inert, waiting to be pulled apart by some future gravitational event. The Moon is evaporating right now at a rate so unimaginably slow that no instrument we will ever build could detect it. But the process is real, the mechanism is real. Space-time curves around the Moon's mass, and that curvature drives pair production at an almost infinitely gentle rate, and the Moon is losing mass. And it will keep losing mass for about 10 to the power of 90 years. That number deserves a moment. 10 to the power of 90. Written out, it's a 1 followed by 90 zeros. The current age of the universe is about 1.4 times 10 to the power of 10. So the Moon will survive for a duration that makes the age of the universe look like less than the blink of an eye. Less than a fraction of a percent of its remaining lifetime. But here's the thing that stops you in your tracks once you've absorbed the mechanism. The Moon will outlive almost every black hole in the cosmos. Not the most massive ones. We'll come to them. But the stellar mass black holes, the ones formed when massive stars collapse, the objects that were supposed to be the last things standing, the survivors of the black hole era, those evaporate in about 10 to the power of 67 years. The Moon lasts to 10 to the power of 90. That's a factor of 10 to the power of 23 longer, 10 to the 23rd. Written out, that's 100,000 billion times as long. The dead Moon outlives the black holes. Let that sit for a second. The object we think of as inert, as essentially over, as a fossil of the early solar system. The object that has no atmosphere, no heat, no light of its own, just rock and craters and the memory of ancient collisions. That object endures longer than stellar mass black holes, longer than the things we were told would be the very last structures in the universe. This is what the density inversion does to your intuitions. Density kills you faster because the mechanism depends on curvature, and curvature is stronger around denser objects. The Moon is less dense than a black hole, less dense than a neutron star, far less dense than any of the exotic remnants we've discussed. And so the Moon's curvature is gentler, and so the Moon's evaporation rate is slower, and so it lasts longer. Simple once you see it, devastating once you really absorb it. Now, here's the part the Radboud team included, I think because they understood how human intuition works and they wanted to make the mechanism as visceral as possible. They didn't just compute the Moon, they computed something closer to home. A human body. Treated as a dense object with a mass and a radius and therefore a space-time curvature around it. A person. You, lying wherever you are tonight. Under the gravitational pair production mechanism, a human body would evaporate in roughly 10 to the power of 90 years. Almost the same as the Moon, which makes sense. The densities are in the same rough ballpark, cosmically speaking. We're not as dense as a white dwarf. We're nowhere near a neutron star. We're soft and slow and not particularly curved. And so we persist, theoretically. Not in any form that's alive, of course. By 10 to the 90 years, the atoms themselves will have long since been rearranged. The chemistry of biology will be an impossibility in a universe so cold and empty that nothing we recognize as life could exist. The figure is illustrative. It's a thought experiment, but it's a thought experiment with a real answer. If you could somehow persist as a dense arrangement of matter, just as you are, The mass of a human body, the density of a human body. Space-time would take roughly 10 to the 90 years to peel you apart, pair by pair. You would outlive the black holes. There's something quietly wonderful about that. Something I don't quite have words for. The mechanism that evaporates the mightiest structures in the known universe, the things that swallow light itself, would take longer to finish you off than it takes to finish them. Not because you are mighty, but because you are, by cosmic standards, not very dense. You are, in the kindest possible framing, a remarkably diffuse arrangement of matter, and diffuse things endure. Now we need to talk about the things that endure longest of all, the most massive black holes, not stellar mass black holes, which form when individual stars collapse. Those sit around 10 to the power of 67 years, roughly the same as neutron stars, and they're gone long before the moon, long before anything as gentle as a human body. The supermassive black holes are different. These are the monsters at the centers of galaxies, objects containing millions or billions or tens of billions of solar masses. The one at the center of our own Milky Way, Sagittarius A star, is about 4 million solar masses. The ones at the centers of the largest elliptical galaxies are larger still. The very biggest known supermassive black holes carry masses of around 10 to the power of 10 to 11 solar masses, tens of billions of times the mass of the Sun. And because Hawking's original evaporation timescales is the cube of the mass, the classic T proportional to m cubed from Hawking's 1974 and 1975 work, refined by Don Page's calculations in 1976, the most massive black holes last extraordinarily, almost incomprehensibly long. For a supermassive black hole of around 10 to the 11th solar masses, the evaporation time runs to roughly 10 to the power of 100 years. That's the classic number, the one you may have heard quoted as the last black hole evaporates after 10 to the 100 years. The number that was, until recently, considered the end of everything. But the very largest, or the giants, the ones sitting at the centers of the most massive galaxies, could last to 10 to the power of 108 years. Longer. The exact figure depends on the mass, and masses vary. But we're talking somewhere in the range of 10 to the 100 to 10 to the 108, give or take, depending on what you're measuring. These are the last things standing after the moon is gone. After you, the diffuse, improbably long-lived, human-shaped arrangement of matter are gone. After the white dwarfs at 10 to the 78 years have finally, gently, completed their long, slow dissolution. After all of it, the most massive, supermassive black holes endure, sitting in a universe that is empty, truly profoundly empty. By this point, nothing else exists. Every other structure has evaporated. The void is complete. There are no galaxies because galaxies are made of stars, and stars are long gone. There are no planets, no moons, no gas clouds, no light from any source, no cosmic microwave background to speak of, no faint photon glow to warm the dark. Even those ancient photons redshifted into effectively nothing by the unimaginable expansion of 100+ order of magnitude future have diluted away. There is, near the very end, almost certainly just one thing, the last black hole. Which black hole it is, we can't know. We don't have a census of every supermassive black hole in the observable universe, and we certainly don't know what the universe beyond our cosmic event horizon contains, but somewhere in the cosmos there is, or was, or will be, a most massive black hole, the one that happens to contain the most mass, and because evaporation scales with the cube of mass, the most massive one lasts the longest, and it is the protagonist of the universe's final chapter. For something close to 10 to the 100 years, give or take whatever the precise mass allows, this black hole sits at the center of its long dead, long dissolved, long evaporated former galaxy. It has been shrinking for almost as long as the universe has existed, but shrinking at a rate so slow that for the vast majority of that time it has been functionally static. An observer standing next to it, if observers existed, which they do not, would see no change from 1 billion-year interval to the next. But the change is there, particle by particle, pair by pair, curvature-driven, just as it is for the Moon, just as it is for white dwarfs and neutron stars, just as it is, in principle, for everything that has mass and therefore curves space. And here is the thing about Hawking radiation. The thing that makes the very end of the universe so strange and so specific. As the mass decreases, the evaporation speeds up. The temperature of the radiation a black hole emits is inversely proportional to its mass. A more massive black hole is colder. It radiates at a lower temperature, more slowly, almost undetectably. But as it loses mass, it gets warmer. And as it gets warmer, it radiates faster. And as it radiates faster, it loses more mass. And as it loses more mass, it gets warmer still. It's a runaway, a feedback loop, an accelerating dissolution. So the story of the last black hole is not a gentle, steady, even fade. It is a process that runs for an almost incomprehensibly long time at an almost incomprehensibly slow pace. And then, very near the end, in the final stages, when the mass has dropped to a small enough value, it accelerates, it warms, it brightens. It radiates faster and faster, and that very speed makes it radiate even faster, and the last moments of the most massive black hole in the history of the universe are its hottest, its brightest, and its shortest. The end comes quickly, after all that waiting. A final burst, a flash, a fraction of a second, perhaps, in its most intense phase, in which the last remaining mass radiates away, in which the last particle goes, in which the space-time curvature that has been the source of the radiation flattens finally, because there is no mass left to curve it. And then there is nothing. Not darkness, not cold, those are still things. States of matter, states of energy, there is nothing. No space curving around any object, no pair production, no radiation, no heat gradient, no structure, no time, arguably, in any meaningful sense, because time as a physical concept is entangled with change, and there is nothing left to change. That flash, that single bright instant, brighter than anything that has existed for 100 orders of magnitude before it. That is the last event in the history of the universe. Now, before we settle into the close, there are a few other possible endings that deserve an honest mention, not because they're likely, and not because the physics demands them, but because the universe hasn't given us its final answer, and science that pretends otherwise isn't quite being straight with you. These are the speculative codas, the other possible last chapters, clearly separated from the Radboud mainline, which is verified work published in peer-reviewed journals. These are different. They're genuine scientific hypotheses, real possibilities, sitting at the edges of what we know, but not predictions, not settled. Handle them gently. The first is the Big Rip. The accelerating expansion of the universe is driven by dark energy. We know that. What we don't know is what dark energy is, or whether its strength is constant over time, or whether it might increase. If dark energy is what physicists call phantom energy, a form with a particular kind of equation of state that causes it to grow stronger over time, then the expansion of the universe doesn't just accelerate gently, it accelerates without bound. And eventually the expansion becomes so rapid that it overcomes every other force. First, galaxy clusters are torn apart, then galaxies themselves, then solar systems, then planets, then atoms. Then, in the final moments, The fabric of spacetime itself tears apart in a finite time singularity. Everything shredded, all at once, no survivors. If the Big Rip is the real ending, then nothing we've talked about tonight. No white dwarf evaporation, no moon at 10 to the 90 years, no final black hole. Any of it happens because the universe ends violently before any of it gets the chance. But here is the crucial thing. We don't know if dark energy is phantom energy. Current observations are consistent with dark energy being a cosmological constant over time, not increasing. The Big Rip requires a specific condition that current data does not confirm. So it's possible, it's a real hypothesis, but it's not the prediction, it's the what if. The second speculative coda is the Big Crunch. This was the dominant worry of cosmologists for much of the 20th century, that the universe's expansion would eventually slow and reverse, that gravity would win, that everything would fall back together into a single point, a reverse Big Bang. We know now from observations of type Ia supernovae made in the late 1990s that the expansion is accelerating rather than decelerating. That makes the Big Crunch seem unlikely given current conditions. But unlikely is not impossible. And there are theoretical frameworks in which the story might eventually reverse. Some cosmological models allow for a turnaround at very large scales, very far in the future. Most don't. But it belongs in the honest catalogue of possibilities. And the third is perhaps the strangest of all: false vacuum decay. The quantum field that gives the Higgs boson its mass, the Higgs field, sits at a particular energy value throughout the observable universe. That value determines a great deal about how matter behaves, but some calculations suggest that this value might not be the absolute lowest energy the field can have. It might be a local minimum, stable for now, but not the deepest stable state. There might be a lower energy state, a true vacuum, that the field could in principle tunnel into. If it did, the consequences would be instant and total. A bubble of true vacuum would form at some point in the universe and expand outward at the speed of light. Inside the bubble, the laws of physics would be different. Particles would have different masses. Chemistry as we know it would be impossible. Life, matter, atoms, everything would cease in the instant the bubble wall passed through. And you would never see it coming. You can't. The bubble travels at the speed of light, which means no signal could outrun it to warn you. One moment you're here, the next moment the rules change and you aren't. This could happen tomorrow. It could happen in 10 to the 500 years. It could never happen. The calculation of the Higgs field stability depends on measurements of the top quark mass and the Higgs mass that have significant uncertainties. Current best estimates suggest the universe is in a state called metastable, technically potentially unstable, but with a lifetime so long that it's not a practical concern by any measure. Possibly stable outright, depending on the precise values of the constants involved. So these three, the Big Rip, the Big Crunch, false vacuum decay, are real science, real hypotheses, real things that could, in principle, happen, but they are not the mainline ending. The mainline ending, the one supported by what we know, the one the Radboud work illuminates and sharpens and brings into focus, is the one we've been walking toward all night. The slow evaporation of dense matter, the long patience of white dwarfs at 10 to the 78 years, the moon at 10 to the 90, the final supermassive black holes at 10 to the 100 or beyond, and the last flash. That is the ending the universe is currently on track for, as best we understand. And now we've arrived somewhere. And I want to just stay here for a moment before the close, before the good night, because there is something I keep coming back to, thinking about this whole arc, something that isn't physics exactly, but that grows directly out of it. We started tonight in the present, in your room, your bed, wherever you are. A universe that is 13.5 billion years old, full of stars still burning, galaxies still forming new ones, a cosmos that feels from the inside like it's in the middle of things rather than near any kind of end. And in a sense it is. It is nowhere near the end. 5 billion years before the sun becomes a red giant, tens of billions of years before the last stars fade, 10 to the 14th years before the stelliferous era closes and the deep dark of the degenerate era begins, 10 to the 78 years before the last white dwarfs complete their dissolution, 10 to the 90 before the moon finally, particle by particle, releases its last bit of mass into the void. And then the black holes, the last great patience, stretching to 10 to the 100 and beyond. By any measure, we are absurdly early, not just early in the universe's story, early in a way that makes the word early seem almost comically inadequate. The universe is 13.8 billion years old. It will produce interesting events until 10 to the 78 years at minimum, probably much longer. We are at the very beginning. The first breath. The very first syllable of what, if it could be narrated, would be the longest story ever told. And that should feel like something. I hope it does. Because what the Radboud result did, what Wondrak and van Suijlekom and Falcke gave us when they published in Physical Review letters in 2023 and followed up in JCAP in 2025, it was not just a correction to a number. It was a reshaping of how we understand the very texture of existence at the deepest level. They showed us that Hawking radiation and the mechanism by which dense objects slowly return their mass to the universe as gentle thermal radiation is not a peculiarity of black holes. It is a feature of spacetime itself, of the way curvature drives pair production. Anywhere the geometry is sufficiently bent. It belongs to the cosmos in a more fundamental way than we thought, not just to the exotic remnants, not just to the horizon-bearing singularities, to everything with mass, to everything that curves space, to the moon, to the earth, to you. You are part of this, not metaphorically, physically. Right now, wherever you're lying, the space-time around your body is curved. Not much, you're not very dense. The curvature is gentle beyond any possible measurement, but it's there. And in principle, the mechanism is running. Pair production, driven by your curvature, at a rate so fantastically slow that 10 to the 90 years is how long the process would take to complete. You are doing what white dwarfs do, what the moon does, what black holes do. You are returning your mass to the universe one pair at a time across a duration that makes the entire history of everything we've ever observed look like a single grain of sand on every beach on Earth. The scale of it is not something the human mind can really hold. We can write the numbers, we can follow the logic, but actually feeling it, actually holding 10 to the 90 years as a real quantity is not something our brains are built for. We evolved to track seasons and decades and maybe a lifetime or two. We are not equipped for this. And I think that's all right. I think not being able to hold it fully is part of what makes it beautiful. The universe is not obligated to be comprehensible to the creatures it produced, that we can get as far as we do, that we can write equations that describe events 10 to the 90 years away, that we can sit here tonight and trace the arc from now to the last flash is already astonishing, already more than we had any right to expect. And somewhere out there, right now, the most massive black hole in the universe is evaporating, imperceptibly, below any threshold of detection we could ever imagine, particle by particle, pair by pair, in a process that will continue for close to 10 to the 100 years before the final acceleration begins. Before the temperature rises, before the radiation brightens, before the runaway begins. And then, After a duration so vast that every word in every language ever spoken by every human who ever lived would not suffice to name it properly, there will be a flash, bright for an instant, brighter than everything else that has existed for a very long time, a last photon, or something very like one, released into a void so complete that there is nothing for it to interact with, a last moment of energy, a last wrinkle in a space-time that will immediately afterward be perfectly smooth, perfectly empty, perfectly at rest. And then nothing. Not darkness, not cold, not silence. Those are still things. Nothing is not a thing. Nothing is the actual absence of anything that could be described. That is the last event. And somewhere in the deep future, somewhere past the white dwarfs, past the moon, past everything we've traced tonight, it happens. Or it will happen. Or it is happening in some sense that physics allows and our intuitions can't quite pass when the timescales involved make causality itself feel strange. It happens. And that is the answer. That is what you came here tonight to find. What is the last event in the history of the universe? It is the evaporation of the most massive black hole, a single flash brighter than anything that has existed in the same vicinity for 100 orders of magnitude, releasing the last energy of the last structured object in the universe into a void that will, after that moment, contain nothing further. Nothing will ever happen again after that, which means that everything that has ever happened, every collision of galaxies, every supernova, every planet that formed and cooled and maybe held an ocean, every moment of whatever it is we're doing right now, here, tonight, you, wherever you are, and Grandpa's voice coming through, all of it is, in the deepest sense, not wasted, not undone by the ending, simply complete. The universe ran. It ran for a very long time, far longer than the old textbook suggested, because white dwarfs are not as stubborn as we thought, and space-time is more inventive than we knew. It ran, and it produced things, and among the things it produced, briefly and early, and under conditions that will not last, was a creature capable of tracing the arc of the whole story and feeling something about it. You, lying there, in whatever corner of the world you've settled into tonight. The universe produced you. And you, in your diffuse, gently curving 10 to the 90-year way, are part of the same story as the last black hole. You are running the same mechanism. You are made of the same physics. The curvature around you and the curvature around a neutron star are different in degree, not in kind. The process is the same. That's not a metaphor. That's the physics. You are a quantum phenomenon in the specific sense that the mechanism Radboud described, pair production driven by curved spacetime, belongs to you as surely as it belongs to anything in this cosmos with mass. It's just that yours is very gentle. And so it takes a very long time, and there's something in that which I find, and I hope you might too, genuinely consoling. The universe is not done with you quickly. Not at this scale. At this scale, the scale where the laws of physics speak their deepest language, where curvature meets pair production meets evaporation, you are one of the more patient structures the universe contains. The toughest, densest, most powerful things dissolve first. The gentle things persist. You are a gentle thing. And you are made of star stuff, as people love to say when you eat. But more specifically than that tonight, you are made of the same space-time curving, pair-producing, hawking mechanism participating mass as every object that will ever slowly fade out of this universe. You are in the story, not as an observer of it, as a participant, a character in the longest narrative ever told. I hope you feel that. Now, wherever you are tonight, whatever room, whatever country, whatever hour, whatever lamp is still on in the corner, or curtain still partly open to the dark sky, I want to come back to where we began. We began with the scale of things, with the fact that the universe's longest-lived stars, white dwarfs, don't last 10 to the 1,100 years the way older estimates suggested. They last 10 to the 78. The end moved up by a factor with over 1,000 zeros. That 3 physicists at Radboud University in Nijmegen found a flaw. Not a cosmetic one, not a small correction, but a fundamental reframing in what we thought Hawking radiation was allowed to do, and that the universe is ending, its texture and its timeline, its cast of last survivors, and the identity of the very final event changed. We walked to the end, we stood at the edge of it, we watched in the mind's eye the most massive black hole complete its impossibly long patience and release the last particle and be gone. And now we've come all the way back to you, to this room, this quiet. The weight of sleep somewhere nearby, I hope, pressing gently. If you've enjoyed this slow journey into the very deep future, if you found something here that settled you or startled you or simply gave your mind somewhere to wander for a while, a gentle like or a subscribe means a great deal to a small channel like this one. Small creators like me really do rely on your support to keep making these long, quiet nights together. And if you'd like to tell me where in the world you're listening from tonight and what time it is in your corner of everything, I read every one of those and I love them. To those of you who've been here before, who've made this a regular thing, thank you. Genuinely. It means more than you know. You've done something generous tonight just by being here. You've let the universe's story be told in your ear in the dark. You've gone all the way to the end of time and come back. Sleep well, wherever you are. The white dwarfs are still there, cooling in the dark, in no hurry at all. The moon is still there, patient beyond all reckoning. And the most massive black hole in the cosmos is evaporating, one pair at a time, in a silence so profound and so distant that it makes the silence of your room tonight feel like a roar. You have time, more than enough. Rest now. Good night, kiddo. Grandpa'll leave the porch light on.